Thanks for joining. I'm going to go ahead and hand things over to our moderator, Jane.
Good morning. Hi, everybody. Thanks for joining us. We are at the Science and Engineering track. And first up, we're going to be talking about what the science is telling us, projection models. We're honored to be joined by two distinguished scientists from the Oak Ridge National Lab in Tennessee. They are Dr. Melissa Allen-Dumas and Dr. Peter Thornton. A quick note on how this is going to work. Both scientists will present, and then at the end, we'll have about 10 or 15 minutes for your questions. You can put your questions in the chat, which is at the bottom of the screen. The black bar, you'll see the chat, and you can just put your questions in there and we'll take them at the end. Okay, I think we're ready to go.
All right, Jane, shall I just take it away here?
Go ahead.
I'm going to do a screen share. And go full screen there. Are you all seeing my slides full screen? Great, thank you. So thanks an awful lot for the invitation to be here today. I really enjoyed the plenary session. First, let me say that was very informative. And I'll tell you a little bit about myself and then dive into a discussion here about what kinds of measurements we have of climate change and what models of climate change are telling us about what we can expect for the future. My name's Peter Thornton. I am a scientist at Oak Ridge National Laboratory in the Environmental Sciences Division, and my work has been primarily focused on land ecosystems, so how the carbon cycle on land interacts with the climate system at a global scale, all the way down to a very fine scale, looking at individual plots and the measurements that can be made by ecologists in the field. I've also worked extensively on the development of computer simulations that allow us to make predictions of future climate as well as past and present climate. And that's my current position at the laboratory, is one of the developers of the Department of Energy's Earth System Model, which is a relatively new endeavor standing on its own, but it has a long multi-decadal history of development going back in collaboration with multiple government agencies. I really enjoy getting out into the field as well as working behind a desk and working on the computer modeling part of this. So I travel to Alaska, I travel to coastal environments and to temperate forest environments to help ecologists who are making measurements in the field so that I can better understand the science and the data that are being collected as I try to develop climate models. So with that introduction, let me just give you a quick overview of what I'm going to talk about for the next 10 minutes or so. And I want to give you some sense of the evidence that we currently have for climate changes of the recent past as well as the historical period. I want to show you a little bit about how those climate changes in the modern era compare with climate changes in the deep past in the geologic record. I want to talk a little bit then about how we understand the causes of recent climate change and what we can say from the scientific point of view with some certainty about what is and is not happening in the climate system today. And finally, I'll wrap this up with what the models are saying about predictions of future climate change and the certainty or lack thereof that we have in those predictions. And then I'm going to turn this over to Melissa Allen-Dumas, who has a presentation about the impacts of climate change. So I'm looking forward to seeing that as well. Now I'm going to focus, because of the shortness of time here, just on temperature. There are a lot of other things we could talk about with climate change. We could talk about precipitation and extremes of precipitation. We could talk about hurricanes and storm events. We could talk about clouds and radiation. But the thing that we actually know the best, that's the best measured and the best understood in the climate system, is the temperature record and the impacts of human activity on that record. I'm going to start with this one plot, which describes the temperature measurements made over the entire globe, the global land area, and shows you going back to 1880 on the left, all the way up to about 2018 is the latest update on this plot on the right. And I'm going to show you a number of different plots that look just like this. But the point that I want to make with these figures is that there is a clear trend. If you start a regression analysis, a line fitting experiment in 1970 and bring it up through the present day, there is a very statistically significant trend of increasing temperature at the global scale. And this is showing about 0.3 degrees Celsius per decade. So that means that in 30 years, you get about 1 degree Celsius warming, and we've had over 1 degree Celsius of warming in that period from 1970 to present. And the next point that I want to make is that this is a globally obvious signal. By looking at that same plot, instead of for the global land, now we're looking at individual regions. So here is North America in the upper left. In the center, we're looking at South America. In the upper right, looking at Europe. In the lower left, at all of Asia. And in the lower right, Africa. Now you can see that there's some variation in the rates of change of temperature in different parts of the world. There's also variation in how variable the rates of the temperature changes are from year to year in different places. But the thing that is common across every region of the globe is that temperatures are rising significantly and detectably over this period. And just a little bit of foreshadowing, the models tell us that there is no reason to expect that this trajectory is going to be any different if we look ahead for the next 30 years on the current trajectory of forcing from fossil fuel combustion that we're on right now. I wanted to just try to put this in a little bit of perspective about—
Peter, I'm sorry to interrupt, but I think we're seeing part of your full screen, but we also see like the next slide and then your notes.
Oh, I'm sorry. Yeah.
Yeah, I don't know if there's a way to go. I'm not sure how that interface works because that looks like a PC.
Yeah, let me, I think what I might have to do is stop sharing and reshare. Let me try this.
Thank you.
Thank you. Yeah, I appreciate that. I'm wondering if
That
that's
looks
in—
good, Peter. You just need to put it in presentation mode.
Yeah, I was, let me try that one more time.
Click on the presentation button, I think. Nope, that's what did it. Okay, never mind. Go back to the way
If
you
you
were.
see, Peter, it says display settings up at the top. Maybe click
Yes.
next. Maybe click that. I'm not sure.
Did that help?
No.
Oh yeah.
There we go.
You good? Okay, I'm sorry about that. I'm going to try to make up the time here. I'll go forward a little bit faster. The figure that we're looking at here is showing the recent changes in temperature on the far right-hand side as in the context of a deep historical record, geologic record of temperature going back hundreds of millions of years. And there are lots of things that have happened in the climate system in the Earth system that have changed the temperature over time. So it's certainly true that the climate can change dramatically for lots of different reasons. This long decline in temperature 50 million years ago is actually the result of the Isthmus of Panama closing and changing the ocean circulations. So that's the kind of variability in the Earth system that we can detect in these global records. As you look in the last million years, of course, there's glacial and interglacial cycles that happen on a periodicity of about 100,000 years. And we have just come out of a glacial cycle, and we are in an interglacial cycle. This panel up to the far right is just showing for the last 20,000 years how climate has warmed and stabilized coming up to the present day. But when you look at that in even more detail, going back a number of a couple thousand years, what we can see is that stability in the climate system with variability superimposed on it has had a significant departure in the recent industrial era. And it's this departure and the rate of change in temperature during this period, which is the real cause for concern. We've had warm temperatures in the past, but we have, in the last million years, not had the rate of change of temperature that we are seeing in the recent decades. And we're quite certain, scientifically, that the cause for this rapid rate of change in temperature is a rapid rate of change in the CO2 concentration in the atmosphere, the major greenhouse gas forcing. And this is just showing you again, over hundreds of thousands of years, there's periodicity in the CO2 concentration in the atmosphere that's connected with glacial cycles. And as you come in closer to tens of thousands of years, you can see that there's quite a long period of stability in the CO2 concentration until you get into the industrial era, when the rate of concentration rises, of course, quite dramatically. And now we're above 410 parts per million. This is one of my heroes shown on the lower right of your screen, Dave Keeling, being awarded the Presidential Medal of Science by George W. Bush for his pioneering work in this area. So finally, we know for a fact that what causes this change in CO2 concentration is the emission of fossil fuel carbon dioxide into the atmosphere. And we also have relatively good records of how much fossil fuel CO2 is emitted into the atmosphere over the past several decades. And this rate has been rising at about 2% per year for decades. And it goes up and it goes down, but the average has been about 2% per year. And there doesn't appear to be any particular slowdown in that rate of rise in CO2 concentration. In addition to fossil fuels, there's also land use and land cover change. And I'm showing you that on the same graph to be able to give you a sense of the relative importance of these. Land use and land cover change is the second most important contributor of new carbon to the atmosphere. And you can see that it is a smallish fraction of the total. The majority of what we see accumulating in the atmosphere is from fossil fuel combustion. The last point that I want to make on this topic is that the amount of CO2 that stays in the atmosphere, having been emitted from fossil fuel combustion and land use and land cover change, is about 45%. The rest of it is taken up by ecosystems on land and by both biological and physical processes in the ocean. So the globe is doing humanity a tremendous service at the moment by taking up 55% of the CO2 that we put into the atmosphere. And if that were not the case, the forcing of our fossil fuel combustion on changes in temperature and other climate parameters would be nearly twice what it is today. So one of the big research questions that we have is, will that that service continue to be provided by the ecosystems of the planet into the future? There are lots of different things that we could look at in terms of indicators of a warming world. I've focused on temperature, but this is just to make the point that there's lots of measurement of various things that we can say for sure. There are impacts occurring throughout the climate system. And I want to wrap this up by just showing you what computer simulations predict about future climate change based on some very sophisticated Earth system modeling that continues to get better year after year, but overall shows two main points. The first point is that we can use these models to show that if you only had natural factors like changes in volcanism, changes in volcanic eruptions, and changes in solar output, you would have a relatively flat climate record as shown here by the green shaded bar. But if you include fossil fuel emissions and land use change, then you end up with a prediction from these models which is able to mimic very closely what the observations show, which is a change in temperature over these decades. And so this is how we are able to attribute the observed changes to particular causes, and in this case, say with certainty that it's us that's causing the majority of the warming that we see. I just want to end by showing you, as we go out into the future, there is a lot of uncertainty if we go from present day, shown here around 2020, out to a century and 2 centuries from now. There's a lot of uncertainty generated by differences in how models are able to make predictions, and that's shown by the gray, wide gray bars around these individual lines. But the biggest uncertainty in this system is actually what we do as a human species in terms of either changing policy, shown by sort of these lower trajectories, or not changing policy, as shown by the upper red trajectory. And the last thing that I will leave you with is that it is important to be able to understand local impacts of climate change, but it is also important to recognize that the impacts of climate change are felt in terms of temperature change all over the planet, and at high latitudes even more than at lower latitudes. So the changes that we see going out to 2100 on a business as usual trajectory will be significant in our local area, between 7 and 8 degrees Fahrenheit potentially, but very, very much higher when we look in the northern latitudes. So Alaska, Canada, Siberia experiencing warming in the 10 and higher degrees Fahrenheit. So that'll have a lot of impacts, and I'm hoping that we are able to avoid those impacts. I'm going to stop there and turn this over to Melissa.
And just while Melissa is getting up and running, please, if you have questions, enter them in the chat box, and we'll try to get to those at the end.
Can everybody hear me?
Yes, we can.
Great, thank you. Oh, and I'm seeing a host disabled participant screen sharing, so I'll need to be given the screen here.
Yep, I'll fix that.
Okay.
So while we're waiting, while we're waiting for Melissa, one of the questions that we got was, is the En-ROADS model useful? Is everyone familiar with the En-ROADS model?
I'm sorry to say that I'm not.
Okay, that is an MIT, born from MIT, and it is allowing regular citizens to go in and play with the different tools that we have available, the solutions that we have available, where you can see what effect the warming will have if, for instance, carbon sequestration is taken to a certain level.
That sounds fantastic, and I will check it out.
Okay, is Melissa ready?
I am ready. Does everybody see my screen?
We do.
Great. And does it look like it should?
It does.
Okay, great. All right, thank you. So, and thank you very much for the opportunity to participate in this conference this weekend. I think this is a wonderful organization, and it's great to get this information out to people and have people participating in this topic here. So I'll say a little bit about myself and then show a few slides about climate change impacts to the U.S. So I am a research scientist at Oak Ridge National Laboratory, and what I study there is mostly the impacts of climate change on critical infrastructure, and that's from the local scale actually all the way up to the national scale. So a couple of projects that I've been participating in recently are, first of all, looking at how a city's morphology, or in other words, the size and the shape and the spacing of the buildings, how that affects the city's microclimate, and then how that in turn will affect the way that people use energy in buildings. And then at the national level, I'm helping to develop a real-time situational awareness tool for the Department of Energy that monitors the health of the electric grid and anticipates the threats and the vulnerabilities to the system, which include climate extreme events and other types of climate issues that can be related to the functioning of the electrical grid. And so today what I'll discuss are just some of the national and local impacts of climate change, and then a few ideas about some local adaptation to and local efforts towards adaptation and mitigation to climate change. So as the Earth warms, as Peter talked about, the effects of climate change are going to be felt in different ways, and in different ways in different geographical locations. And so the U.S. Climate Assessment outlines several impacts of climate change that are sort of emerging across the country. And these observations are noted in the different weather stations and measurement satellites and buoys in the ocean. And all of these are pointing, even as you saw in the presentation that Peter showed, they all point to that, that the world is warming. So with this warming, we see changes in precipitation patterns, sea level rise, oceans are becoming more acidic, and then the frequency and intensity of the extreme weather events are increasing. And then we also know that climate change does not occur in isolation. It's superimposed on other stresses. And one of those stresses is the fact that the population is growing and demanding more of the Earth's resources. So here's a sort of a schematic of how climate can affect lots of different aspects of the way that we live. One of the main ways that it does affect our livelihood is in the way that it can affect energy generation and energy demand. And so, for instance, changes in temperature will increase demand from the citizens. As the population grows, there are more people who are needing this energy. It can respond to changing economic considerations that can also sometimes be influenced by climate change. Also, for instance, if the temperature is too high in a certain area, that will put an additional stress on the load that a transmission line can take. And so as those are more stressed and different patterns of transmission emerge as a result of that, then different parts, then there can be blackouts, and different parts of the whole system can then shut down and sort of cascade into different effects throughout the entire infrastructure sector. But nationwide, here are a few things that are happening as a result of climate change itself. So, for instance, with the increase in extreme weather events, we have storm surge, we have sea level rise, we have heavy precipitation patterns, and you can see on the right-hand side there, a nuclear facility has been flooded. And at that time, then it is unable to generate the power that we need. On the left-hand side, we see an image of a city that's under a heat wave here, and I think we've probably all seen in cities some of these sort of bumps in the road that occur when the pavement is heated up enough that when the traffic goes by, the pavement itself begins to shift. And additionally, you can see some of these results from extreme heating in the rail lines. Those can tend to sort of be a little bit wavier after extreme heat events as the trains are going across, and some of the weight is shifting from side to side. That will then affect the rail lines if it's hot enough. And so all of these things are affecting then certainly the way that we move around in these spaces, but then also it will attacks the cities or the states or those who are tasked with doing these repairs. So another way that climate change is affecting us is that it has impacts on human health. So as we get either more rain or drought situations or different runoff situations, we can show a decrease in our water quality. And so we need to make sure that we're maintaining the water correctly there or in the most healthy way. As the air warms, it can become more stagnant, and so it can retain more of the pollutants and smoke and various different irritants to people's nasal systems, and certainly if people have asthma, those will be exacerbated by those conditions. Likewise, extreme temperature can affect people in buildings that don't have adequate air conditioning, and it has in many cases led to deaths in areas where people are not able to get cool under a heat wave. And certainly we've seen in California recently the impact of the wildfires there, which are sort of a result of the drought that California has been seeing, and there have been deaths associated with that. So there's all kinds of impacts on human health as well. So, so one of the things that we have to ask ourselves is how can we adapt to climate change? And so there are various different pockets of organization around this all over the country, and certainly this community here that's meeting today has done a lot of looking into these things, I believe. So, but one example is a risk matrix that was adapted from the Port Authority of New York and New Jersey. And what they began to look at is there are certain expectations with extreme events that are coming as a result of climate change, and they mapped out what would be the magnitude of the consequences there, but then also the likelihood of occurrence. And once they were able to get this matrix sort of set up, they could then determine how to address the things that are most likely, in the most immediate future, but then begin to plan for things that are unlikely but extremely damaging should they happen. And so this sort of thing provides an example for some smaller communities being able to organize and to set up some adaptation changes. And one of those communities that has begun to do these things is the Knoxville area. So they certainly believed, and we certainly believe too, that in order to undergo certain adaptation and mitigation changes, that partnership is key. So we think that citizens are important in that partnership. We also believe that the researchers both in academia and national labs are important, and then the federal and the state and the local government, some of them being government agencies and others just being our Congress people or our mayors or the people that care about these issues and want to help make a difference. And you can see over here on the right-hand side, we go, whoops, my screen is very touchy here. But on the right-hand side, you can see going all the way from very local, which is just a transmission tower there, and then going all the way up to the global, these partnerships and gatherings together of knowledge and study and action can really make a difference. So one of the things that I'll tell you a little bit about today is a partnership between ORNL and the city of Knoxville that was undertaken a couple of years ago. What we did is we recognized that one of the issues that we will have to face in Knoxville as a result of climate change is extensive flooding. So we developed a tool that would cite specific places in the town where we could put some green infrastructure that would help with soaking up that water when it comes. And so there were certain vegetation recommendations that were made and certain locations that were more ideal than others for that. And we were able to locate them with this tool. We also took a look at where it would make a difference to put permeable pavers in the city. And one of those places that we found was really the middle of downtown. And so as that was being revitalized recently, the sidewalks were replaced with these permeable pavers instead of the sidewalks that we had had before. And they've already begun to make a difference. And so that was one way that we could begin to work on adaptation for the city of Knoxville. And then,
Hey, Melissa, I
yeah.
hate to interrupt, but we've got less than 10 minutes left, and I want to make sure we have time for a few, at least, questions from the audience. So I'm not sure if you're or close to wrapping up, or if you're able to kind of wrap up, but I'd love to save a little bit of time for questions.
Oh, absolutely. And this is my last slide. So,
okay,
and this, I'll just tell you a little bit about this. And this is actually a way that Knoxville, the Mayor's Council in the city of Knoxville is actually working towards mitigation of climate change. And so I don't know if I've got some, the stack of videos on my right-hand side of the computer, but if you're able to move that and see underneath there that there are different CO2 emissions targets that Knoxville has set for itself. And it is looking into both the transportation sector, the building sector, and also then the waste management sector to find ways that they can direct those different parts of the city functions towards fewer emissions and ultimately reaching these emissions goals. And so I'll leave you with that, and we'll open it up for questions.
All right. We have a couple from the chat. One of the questions was about carbon capture technologies. Are we closer to fruition besides just tree planting? And what do you think about that?
Melissa, I'll take a quick stab at that. And I do believe that we are going to get into a scenario where carbon capture, not only from fossil fuel combustion streams, but actually free air capture from the atmosphere is going to be necessary to meet the kind of concentration trajectory in the atmosphere that we will want to see. And lots of different technologies are being explored. It's much simpler to pull CO2 out of a combustion stream than it is to pull it out of the air because of the very low concentration of CO2 in the free atmosphere. But there's a lot of research underway right now, including at ORNL, to begin to explore how to improve the efficiency of that process. And I personally believe that we will find ourselves in a place where that is necessary.
Okay.
Yeah, and I'll just add to that as well too, that there's initiatives going on at ORNL as well to look at carbon capture and conversion. So capturing CO2 either from the industrial streams or from the ambient air, they can then turn this into additional fuel. So they've sort of been able to make a good product out of something that may have originally been more damaging.
That's really positive and hopeful. I wonder about the timeline on it. Do you have a sense of that?
Capture from...
okay.
Go ahead.
I was just going to say, some researchers have already made that possible. Now, whether that transitions into being done on a large scale, I'm not sure what that timeline would be. But definitely the research has shown that it is possible to do the conversion.
Okay. Another question. You had mentioned that 2% per year of warming per decade is happening. Is it safe to say that we're now seeing impacts much quicker than the scientists were predicting just 20 or even 10 years ago?
Actually, the models, if you go back 30 years and look at the history of climate prediction, although the range of predictions has shrunk, the mean prediction is actually not very different from what we are seeing today. The models have more or less gotten the temperature change predictions based on assuming what the concentrations of CO2 are in the atmosphere on average, right, over time.
Okay. What also do you think about nuclear power in terms of being an effective tool?
I'm a big fan of every possible solution that we can throw at this problem. And I think it is a case where we can't leave anything on the table here. I'm sorry, can't.
Yeah, I second that.
We have to have everything on the table.
Right.
I'd like to make an advertisement for the next session, which is about different sources of non-carbon electricity. So just stay on the line and you'll hear even more.
Okay. I also wanted to mention that we hear a lot as climate activists that the most effective way to talk to people about climate change is to make it local. And I really liked what you did, Melissa, with, you know, bringing the efforts that you've put into your work out into the community. Can you say a little more about that? Is it the responsibility of the scientists? I guess that was the question that was in the chat, to educate the public on their findings.
I found that that's one of the most exciting aspects of this work, is understanding that it can be used directly in the community, and it can make a difference directly in the community. And I really applaud what the city of Knoxville is doing with their initiatives along these lines, because they really are making decisions for the sustainability of that city. And then ultimately, I think that can be an example for other cities in this country that can begin to make a difference at that level that will aggregate up to, you know, a global difference.
Okay. Another question. There are two bills in Congress that seem to be particularly important to getting legislation that will directly begin to reduce the impacts of climate change. Are these two bills complementary? Should one be given priority over the other, or should they both be strongly supported at the same time? Are there other bills of equal urgency?
Melissa, I'll take a crack at that. I think the two bills that are being referred to are the Green New Deal, like omnibus sort of, and the one that CCL itself is
HR 763.
Yes, Carbon Dividend, Energy Innovation and Carbon Dividend Act. I've been fortunate through my connection with CCL to hear from the economists about that particular bill, and it sounds very encouraging to me. I like the specifics of a plan that focuses on both incentivizing and capturing what the economists call the external costs of polluting the atmosphere with CO2. I think that sounds to me very, very rational.
And just sorry to interrupt again, but we've got about a minute left. So once we wrap up, we'll have to transition, and I'll have to give you all the boot and get ready for the next one. But I just wanted to say that quickly.
Okay. Do we have time for one more question?
I think so. Yeah.
Okay. The lowest temperature increase is greater than 20 degrees C by 2100. Will the damage done by this increase be a livable planet?
Melissa?
Okay, that's a tough one. I think that there are lots of ways that we need to adapt even now, and I think if we can harness those adaptation measures and be able to expand them, we can possibly adapt to that. But I think we're going to have to use a lot of mitigation measures as well to really keep it a livable planet.
Okay, I just want to wrap up by saying thank you so much to our guests, and thank you all for being here. And now we're going to transition. We take a little break and then go to the next part.
Thank you very much.
Thank you all.
Thank you very much. Bye-bye.